So in today's lecture, we will do section 1.6, more on linear systems and invertible matrices. Okay, so let's start with the following theorem. So a system of linear equations has 0, 1, or infinitely many solutions. Okay, and there are no other possibilities. So in the past lectures, we have seen a system of linear equations that has no solution. We have also seen a system where there is exactly one solution, and we have seen a system where that system has infinitely many solutions. Okay, we have seen all these examples from before. So what we actually need to prove in this theorem is that there are no other possibilities, meaning there is no system in which there's exactly two solutions. Okay, or there's no system that has exactly three solutions. Okay, so those guys there are not a possibility. Okay, so how do we prove this? There are no other possibilities. Okay, so suppose, let us consider a system. So what we're going to do is to write the system in this form. Ax equals b, okay? Where A here, it's the matrix of coefficients of the system. X here is your coefficient vector. Your variable vector. And then B here is your constant vector, okay? So we have Ax equals b. So let this be a linear system, okay? So to prove that there are no other possibilities, okay, we will assume that this system here has more than one solution, okay? So let Ax equals b be a linear system, and suppose let us get two solutions. So suppose, let me put this as x sub 0, okay, x sub 0 and x sub 1. Suppose these two guys are solutions of Ax plus b of that system, okay? So what does this mean? Then we have the following. We have A x sub 0. This is equal to b. And we also have A x sub 1. X sub 1. This is also equal to b. Okay? That's what it meant if you are a solution, or if an object is a solution. It must satisfy the equation. So this is a linear system. This is a matrix equation. These two vectors, x0 and x1, are solutions, or we assume that they are solutions. So they should satisfy um, this matrix equation. Okay? Now, this is what we're gonna do. Then, okay, what we're gonna do is the following. Let t be any real number, okay? So let t be any real number, and let us put this guy here, put x sub 2, okay? X sub 2 to be, or X sub t, I'll write X sub t. So X sub t to be X sub 0, okay? X sub 0 plus t, X sub 1 minus X sub 0. Okay? So far, so good. Of course, you see here, if X, or if t is equal to 0, if t equals 0, then clearly we see X sub t, which is 0 now, or X sub t, I'll put X sub t. X sub t, this is X sub 0 plus 0 times that guy, this vector here. X1 minus X sub 0. Okay? Which is just X sub 0. Okay? So let me write this as, this is equal to X sub 0. If t equals 1, then your X sub t, so X sub t, this is X sub 0, plus, this is t equals 1, you will have X sub 1 minus X sub 0. Okay? And this will be equal to X sub 1. So far, so good. Now, I did not mention in here, but we are assuming X sub 0 and X sub 1, they are different, they are distinct solutions. Okay? So suppose X sub 0 and X sub 1 are solutions, meaning we assume that they are distinct. Okay? They are distinct solutions. Okay? So maybe let's put that. Let's add that condition. So X sub 0 and X sub 1 are distinct solutions. Let me put that. So distinct. So you insert that guy there. Therefore, if they are distinct, this X sub 1 minus X sub 0, this is not equal to 0 because they are distinct. Okay? Now, what we're going to do is the following. Then, let us write it here. Then, we have X sub A, X sub 2. Okay? We have A, X sub 2. If you recall that X sub 2, let us go back to that slide. X sub 2, sorry, I don't have X sub 2. I have X sub t in here. I have X sub t. So in here, let us replace this X sub t. The X sub t in here is given as this guy here. Okay? So we will have quantity. We have quantity X sub 0 plus t X sub 1 minus X sub 0. This is a matrix. This is just a vector. So they are they are matrices also. So we can distribute this matrix here. So this is equal to Ax sub 0 plus, this is a scalar. The t is a scalar here. It's any real number. So it can go in and out of products of matrices. So in particular, we will have here a t times a x sub 1 minus x sub 0. Okay? And then x sub 0, it was a solution. Okay? X sub 0, it was a solution of this equation. Therefore, this equation is satisfied. Same is true with x sub 1. Okay? It's also a solution and this is satisfied. And again, x sub 0 and x sub 1 are distinct, which means that this guy here, a x sub 0, this is just b. And then plus t. For this guy, let's just um, distribute that so that you will have a x sub 1 minus a x sub 0. But then again, you will have b plus t. And then in here, ax sub 1, that's also b, minus ax sub 0, that's again b. B minus b, this is equal to 0. 0 times t, that's again the 0 vector. And therefore, we will just have here b. Correct? So what does this mean? This x sub t is also a solution. Correct? But how many t's do you have in here? There are infinitely many t's because t is any real number. Okay? So x sub t is also a solution. Okay? And in fact, there are infinitely many solutions. So there are infinitely many solutions. There are infinitely many solutions. Okay? Don't have space. Let me just adjust this guy here. Okay, so if there are infinitely many solutions, it means that if you found two solutions, okay, you can actually find infinitely many of them. If you found three solutions, you can find infinitely many of them. So there are no other possibilities. We saw a system with zero solution. We saw a system with one solution. Okay. Now, if you found that a system has two solutions, then there will be infinitely many of them. You just need to find them all. And one way to find another solution is to do this thing here. Okay. So this is the proof of that theorem, of this theorem. Okay. Questions? Okay. Next. So we have the following. If A is an invertible n by n matrix, then for each n by 1 matrix P, the system of equations Ax equals P has exactly one solution. And this solution will be of this particular form. X will be A inverse B. Okay? So again, if A is an invertible matrix, take note of that. If A is an invertible matrix, then for each n by 1 matrix B, the system of equations Ax equals B has exactly one solution, and the solution will be A inverse B. And since we are talking about invertible matrix, the matrix is a square matrix. Okay? So how is this proved? It's written here actually. The proof is left as an exercise. Okay? you need to show two things. Show that there is a solution, okay? So show that this system has a solution, and then show that there is exactly one solution, okay? Meaning, if you got quote unquote two solutions, then the solutions that you obtain, they are actually the same. They are exactly the same. Okay? So this theorem has two parts: existence and then uniqueness. That's what you need to show for this theorem. Okay? Find the solution set of the linear system. So the linear system, it's x plus 2y plus 3z equals 5, 2x plus 5y plus 3z equals 2, x plus 8z equals 8. So we can do this using your Gauss-Jordan method, okay? Or we can do this by checking whether the matrix of coefficients is invertible. And if it is invertible, you can use the inverse and multiply it to this vector to get your solution. Okay? Of course, at first you will just do the Gauss-Jordan method and get directly the solutions of this. Okay? But look at this. You have this system with this right-hand side. The other one, suppose we change it to another vector b here. Okay? So, of course, you will not do the steps again that you would have done in this part. Okay? You can augment this guy here with the matrix of coefficient here. And at the same time, you can also augment this guy here. Okay? So you just have to augment all those vector b if you have a lot of vector b. Okay? Or you can just get the inverse of the matrix of coefficients. And once you know that, whatever your b is, whatever your matrix b is, just multiply it. Okay? And of course, that's in the assumption that your matrix of coefficients is invertible. So let's look at this matrix of coefficients. So the matrix of coefficients is matrix of coefficients, okay, is, let us look at this. We have here 1, 2, 3, 2, 5, 3, 1, 0, 8. So this is the matrix of coefficients. And what we're going to do, of course, check whether this is invertible, okay? Or maybe, let's do this directly. Find the inverse of this immediately. Of course, if we cannot find the inverse, we will fail. It means this matrix is not invertible. On the other hand, if we do our process and found the inverse, then we're done. At least for the first part. Okay? So let's find the inverse here. So what we're going to do is to augment this with the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we apply our Gauss-Jordan method. So for the first, okay, so for the first here, this is a leading one already, the leftmost entry. So we can fix this. We can use this as our top row. That's your step 1. This is a leading one. Step 2, we are also done. Step 2 is interchange. This is already on the top row. So step 2, we are done. Step 3, this is already a leading one. So we are also done with that. We now go to step 4. Step 4 is, since this is a leading one, we want all the entries below this leading one here to be 0. So we now uh, use, or we now apply elementary row operations so that we make this 0 and this 0. Okay? So first, we can replace row 2 by row 2 minus 2 row 1. And then we also replace row 3 by row 3 minus row 1. Okay? So in here, we have the following. Actually, instead of using this as our top row, I want to interchange it with 108. Okay? I want to interchange this top row with 108. The reason is I already have 0 on this part. So that will reduce our computation later. Okay? So before doing this guy here, you will see that we will use the same elementary row operations. Okay? But before doing that, let us interchange row 3 and row 1. So if we do this, we will have 108 and then 253 for the second row. The third row will be 123. Okay? And then let me just put here now the augmented matrix form here. I'll use color blue for this side. So interchange row 1 and row 3. We will have here 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay? And then at this point, now we will do that the same. Uh, we use the same elementary row operations as what I have written earlier. So it's row 2 minus row 1 and row 3 minus row 1. So for this, row 1 here, it's fixed. 1, 0, 8, 0, 0, 1. And then row 2 minus row 1, that's 2 minus, sorry, why just row 1 here? I'll use 2 row 1. My bad. So twice the row 1. So in this case, we will have 2 minus 2 times 1. So we will get immediately 0 there. Then here you have 5 minus 2 times 0. So 5 minus 0, that's still 5. In here, we have 3 minus 2 times 8. So 3 minus 16. So that will be what? Negative 13. Okay? And then for this guy here, we have 0 minus 0. That's still 0. 1 minus 0, that's still 1. And then 0 minus 2 times 1, we have negative 2. For the third row, we have 1 minus 1. That's 0. And then 2 minus 0, that's 2. And then 3 minus 8, that's negative 5. And then 1 minus 0, That's 1. 0 minus 0, that's still 0. And then 0 minus 1, that's negative 1. Okay. Now I think I am regretting doing this. But anyway, let's continue. Let's continue with this path. The reason why I am regretting is that, look at this. This is the leftmost entry from between row 1 and row 2. This is the leftmost entry. This is also the leftmost entry, which are not zeros. So they are on the same column. If I divide this row by 5, I will get some fraction here. If I divide this row by 2, I will still get some fraction here. So that's, well, that will just complicate our solution later in a sense that we will be dealing with fractions. But anyway, let's own it. Okay? So I'll just fix this 5 in here. I'll just divide row 2 by 5. So this will be 1/5 row 2. And also, I'll just divide row 3 by 5 by 2. I mean. Okay? So we divide row 3 by 2. So at this point, I will need a bigger set of brackets. But anyway, we're not going to touch row 1. So we'll just have 1, 0, 8. We still have here 0, 0, 1. For the row 2, we just divide it by 5. So we will have 0, 1, and then negative 13 over 5. In here, we have 0, and then 1 over 5, negative 2 over 5. For row 3, we divide it by 2. We will have 0, 1, negative 5 over 2. In here, you have 1/2, and then 0, and then negative 1/2. Okay? Then, this is a leading one. We can just subtract this from this. Oh, sorry, we can subtract this row 3 from row 2. So we have row 3 minus row 2. So again, row 1 is fixed. 1, 0, 8. Okay. You have here 0, 0, 1. For the second row, we still have 0, 1, negative 13 over 5. And then 0, 1 over 5, negative 2 over 5. For the third row, we now have 0 here. And then 1 minus 1, that's 0 there. And then in here, minus 5 halves, minus negative 13 over 5. Let me just put the calculation down here. So minus 5 over 2 minus negative 13 over 5. So it becomes plus 13 over 5. So if we continue with the calculation, LCD, it's 10. So this is negative 25. And then here you have plus 26. So this is just 1 over 10. So this guy here, it's 1 over 10. Okay. And then what? For this guy, you have 1/2 minus 0. So you have 1/2. And then 0 minus 1/5. That's negative 1 over 5. And then for this, we have negative 1/2 minus negative 2/5. Again, let me put the calculation in here, but I hope you already got this calculation. If not, just do it. I'm gonna erase it to save space. So this time, we have negative 1/2 minus negative 2 over 5, so that's just plus 2 over 5. Again, LCD, it's 10. This is negative 5, and this is 4. And therefore, we will get negative 1 over 10. So here we have negative 1 over 10. Okay? And now we're good so far. What we're going to do is to multiply this third row by 10. So we will cancel the denominators here, and we'll just get integers. And we're back to having a nice matrix again, at least nicer than this current form. So let me copy this and go to the next page. So we have it here. So as I have said, we multiply now third row by 10. So if we do this, we just copy row 1, 1, 0, 8. And then in here, we still have 0, 0, 1. For row 2, we just copy it, 0, 1, negative 13 over 5. And then here you have 0, oops, 0, 1 over 5, negative 2 over 5. And then for the last row, we multiply by 10. So we will have 0, 0, 1. 1/2 times 10, that's just 5. Negative 1/5 times 10, that's negative 2. Negative 1, 10 times 10, that's just negative 1. And then we now go to step 6. We want to make the entries above this leading one. We want to make them 0. So for the second row, what do? We have row 2 plus 13 over 5 row 3. Okay? 13 over 5 row 3. So that if I multiply row 3 by 13 over 5, this guy here will be 13 over 5, and it will cancel this once we do the addition. That will be row 2. For row 1, we will have row 1 minus 8 row 3. Okay? So, we just copy row 3, 0, 0, 1, and then 5, negative 2, negative 1. Okay? For row 1, we have row 1 minus 8 row 3. So this is 1 minus 0, that's 1. 0 minus 0, that's 0. 8 minus 8 times 1, that's 8 minus 8, that's 0. Then 0 minus 8 times 5, that's minus 40. And then 0 minus 8 times negative 2, that's positive 16. Then 1 minus 8 times negative 1, that's positive 9. And then for row 2, we do this. So we expect here 0. We have here 1. That's 0 minus 0, 1 minus 0, or 0 plus 0, 1 plus 0. And then in here, we have negative 13 over 5 plus 13 over 5 times 1. So this will be 0. For this, we will have 0 plus 13 over 5 times 5. So this is just 13. Okay? So 5 times 13 over 5, that's just 13. So 0 plus 13, we'll get 13. And then in here, let us do the calculation here. So you would see we have 1 over 5 plus 13 over 5 times negative 2. That's this guy minus 13 over 5 times negative 2. So you will see this is just 1 over 5 minus 26 over 5, and 1 minus 26, that's minus 25 over 5. So this is negative 5. So we still have an integer in here. Okay? And then for the last guy there, we have negative 2 over 5. So negative 2 over 5. And then in here, you have plus 13 over 5 times negative 1. So negative 2 over 5 minus 13 over 5, this is negative 15 over 5. And that's equal to negative 3. Okay, dokie? So although we did some fractions in here at the end, we are very lucky. We got integer entries in here. Okay? So whether you did this path or from here you immediately do this, you should get the same final answer. Okay, you should get the same final answer. And maybe if we didn't do this part, if we did the first set of elementary row operations, the one that is the first method that that I was about to do earlier. So if I didn't do this part here, maybe I wouldn't suffer with these fractions. Maybe, just maybe. But anyway, at least we have found the RREF, and this part here is a matrix with integer entries. Okay, but this also means that the matrix of coefficients is invertible. Okay, so if this guy here, if this matrix here, okay, if we label this as our matrix A, okay, so the matrix of coefficients A is this guy here, then we have A inverse. So A inverse, it's this matrix here. So negative 40, 16, 9, 13, negative 5, negative 3, 5, negative 2, negative 1. So what about this? Our goal is to find this linear system. And according to a previous theorem that we proved, um, actually we proved it offline, not recorded. it means that all we need to do is to multiply this matrix A to this vector 5, 2, 6. Okay? So therefore, the solution to the system, or the solution of the system is we have the matrix A, which is 4 or negative 40, 16, 9, 13, negative 5, negative 3, 5, negative 2, negative 1. We multiply this to 5, 2, 6. And let's just do the multiplication here. We have negative 40 times 5, that's negative 200. 16 times 2 here, so that's plus 32. And then 9 times 6 here, that's 54. Okay. For the second row, or the second entry, 13 times 5 here, what is this? 65. So we have 65 plus negative 5 times 2, that's negative 10, plus negative 3 times 6, that's negative 18. Then for the last entry, 5 times 5, that's 25. Negative 2 times 2, that's negative 4. Negative 1 times 6, that's negative 6. So if we simplify this, we now have the solution to the system. Let's just simplify this. So 32 plus 54, that's 86. Okay, 32 plus 54, that's 86. So 86 minus 200, that's negative 114. Please check my arithmetic there. And then here, 65 minus 10 minus 18. So minus 18 minus 10, that's minus 28. 65 minus 28. What would that be? We have 37. And then in here, we have 25 minus 4 minus 6. So 25 minus 10, that's just 15. So this is the solution to this linear system. Okay? So for this problem, again, looking at this problem, we have the same left-hand side. We have a different right-hand side. So to solve this, we'll just get the inverse from here. So let me just copy this matrix here. Copy. And then put it here. Paste. So let's just write here from the previous example. From the previous example. Okay. If A is the matrix of coefficients, if A is the matrix of coefficients of the system, then we have that A inverse. Okay. Then we have this. So the solution. So the solution to the system above, so this system here. So the solution to the system above is you have this matrix, negative 40, 16, 9, 13, negative 5, negative 3, 5, negative 2, negative 1. We just multiply it to 1, negative 2, 3. Okay? And you will get your solution. So I leave the computation to you. Okay? So you have this guy here. I mean the solution to this system here. Okay? Any other questions? Okay. Let us now consider this theorem. So let A be a square matrix. If B is a square matrix such that BA equals I, then B is the inverse of A. Also, if B is a square matrix such that AB equals I, then B is the inverse of A. So remember, when we first defined the inverse of a matrix, we needed to check two things. We needed to check that BA equals I and AB equals I. Although later on that day, okay, after quite some computation, I was only checking one of them. I just checked BA equals I and then concluded that we have the inverse already. That's because of this matrix. That's because of this theorem. This means that you actually really need to check only one of them. You don't have to check both. You just need to check one of them. Okay? So how do we prove this? I will prove A. Okay? I will prove A. For letter B, I will leave that as an exercise. Okay? So, we have a square matrix A, and we have a matrix B, a square matrix B, satisfying this condition. Okay, so let's have that. Let B be a square matrix. So be a square matrix such that BA equals I. Okay? So how do we prove that B equals A inverse? What we're going to do is the following. We will consider a linear system. Okay? We try to consider a linear system that goes something like this. So consider the system be a X. This is let us consider this, actually not this guy, actually not this system. This system, we consider the system AX equals 0. Okay? So this is a homogeneous linear system. Okay? Of course, this will have at least one solution. Correct? this one has at least one solution. The trivial solution is always a solution of a homogeneous system. The question is, are there other solutions? We will show that there's no other solution. Okay? So here, let x sub 0 be a solution of that system. Be a solution of that system. Ax equals 0. Okay? So we don't know the form of x sub 0 yet. Okay? But we know that when we evaluate a x sub 0, when we put this x sub 0 and multiply a to that, this is equal to the 0 vector because it's a solution. Okay? Because it's a solution. It means that this guy here satisfies this equation. Okay? And then, what we're going to do now is to multiply the matrix B. So we have BA x sub 0. This is B times the 0 vector there. Correct? So here, initially you have this grouping. And then here, B times the 0 vector there. This is equal to the 0 vector here. And then we just regroup this. We'll have BA times x sub 0. And then this is the 0 vector. But according to this, BA is equal to the identity matrix, which means this is just I x sub 0. And therefore, x sub 0, now we know it's just the 0 vector. Okay? We now know that it's just the 0 vector. Follow so far? But now, x sub 0, we chose it to be any solution of ax sub 0. Ax equals 0. It was arbitrarily chosen. Okay? And then we just found out that although we arbitrarily chose that x sub 0, we found out that it's just the 0 vector. So what does this mean? X sub 0, which is the 0 vector, if you chose another, say x sub 1, you do the same method in here, your x sub 1 will still be the 0 vector. So what I'm saying here, the only solution of this system, of the homogeneous system, is the 0 vector. So this means the only solution of that system, Ax equals 0, is the trivial solution. Okay? Follow so far? Now, we have this. We have the trivial solution only as the solution of a homogeneous system. A here, it's a square matrix. So what does this mean? The matrix A is invertible. Okay? This means that A is invertible. And now we know that it is invertible. We can now show that that B equals A inverse. Okay? So we are now on the last steps. Thus, from BA equals I, okay? All we need to do is just to multiply the inverse of A on the right, okay? One has, so you have BA times A inverse. This is equal to I times A inverse. Regroup A, so B times A inverse. And then in here you have I times A inverse, that's still A inverse. But this guy here, it's your identity. So you now have BI, that's equal to A inverse. And finally, B is simply A inverse. And that's what we want to show. Okay? So this completes the proof of the theorem. Okay? So again, I am leaving B as an exercise to you. You will also do almost the same argument. Okay? You will still consider a matrix, a linear system, a homogeneous linear system, and then show that you will have only the trivial solution. Okay? And then once you have the trivial solution, then the matrix of coefficients um, in your linear system, the one that you considered, will be invertible. And therefore, you will be able to show this guy here. Okay? So that's how you're going to do that. So now we have these equivalent statements from the last lecture. Okay? A is invertible if and only if AX equals 0 has only the trivial solution, if and only if the reduced row echelon form of A is the identity matrix, if and only if A is expressible as a product of elementary matrices. Okay? So, by the way, I have not shown um, the say quote unquote graphical representation of this. Um, or yeah, but let me show what this statement, the following are equivalent, means in terms of these letters A, B, C, and D. So this means that you have your A if and only if B. Okay. So if A is true, then B is true. Also, if B is true, then A is true. But this guy here, going to this part, if B is true, then C is true. And also C, if C is true, then B is true. And therefore, you have that connection. So if A is true, then C must be true. And then if C is true, then A must also be true. Okay? And then you have the letter D. So same thing. That's one way to write this. Another way to write this is that you have A, B, C, D here. So A, that will imply B. But this B will imply C. Also, this C will imply D. And furthermore, this D will also imply A. And therefore, B implies A can be seen as from B, you go to C, you go to D, and then you go to A. And therefore, you will have this other direction in here. Okay? And then you also have this direction in here. You also have this direction in here and this here. And you also have this direction there and also this direction here. So everyone is true or everyone is false. Okay? Now, we had these 4 statements. What we're going to do is to add 2 more. Look at this. AX equals B is consistent for every n by 1 matrix B. Also, AX equals B has exactly 1 solution for every n by 1 matrix B. And where is this coming from? Remember, A is invertible. Okay? A is invertible. Then this system will have exactly 1 solution. That's what we saw. That's what we saw in here. If A is invertible, then for each matrix B, for each n by 1 matrix B, the system has exactly 1 solution. Therefore, this system here is consistent. Okay? The question is, if we have this guy here, if AX equals B has 1 solution, has exactly 1 solution, how do we show that A is invertible? And once we've shown that one, then all of these, again, will be equivalent. Meaning, if A is true, B, C, D, E, F will be true also. If D is true, F will also be true, E will also be true, and all of the other statements. Okay? So it's enough, maybe, when you want to prove this, it's enough to show that, for example, you can prove that if E is true, then D will be true. Okay? Or maybe if E is true, then C will be true. And then if C is true, E will be true. You can do that. And once you've established that, then the 5 of them will have the same truth values. They are all true or they are all false. That's what you can also do for letter F. You just show that this letter F is equivalent to one of the other 4. Once you're done with that, then all of these 6 statements here are equivalent. Okay? So I will leave the proof to you. Okay? You can practice on that. The equivalence of all of them. So if you assume A, that should imply B. If you assume B, that should imply C. If you assume C, that will imply D. And now from here, you can show that if you assume D, that will imply A. That's the first 4 statements that we had. So the 4 of these are equivalent. If we now consider E and F, we'll have to find which is the easier path. Is it E implies A, or A implies E, or A implies F, etc. So try to search on how to prove the equivalence of this. Okay? Next theorem here. Let A and B be square matrices of the same size. If AB is invertible, then each of the factor here, the factor A or factor B, must also be invertible. Okay? So if AB is invertible, then A and B must also be invertible. Previously, this is what we had. If A and B are invertible, okay, then the product will be invertible. Then AB is invertible. This statement is the converse of that. We start with the fact that AB is invertible. And then we must show that each A and B is invertible. Okay? So I'm leaving the proof of this theorem as an exercise. So if you have a copy of our reference book, you'll be able to read it there. Okay? Next, we want to know if a system of linear equations is consistent or not. So the fundamental problem is, let A be an m by n matrix. Take note, our A, it's not a square matrix. Necessarily, it's not a square matrix. Or I think that my statement is confusing there. What I mean is that your A may not be a square matrix. So our problem is we want to find all possible m by 1 matrices B such that the system of equations AX equals B is consistent. Okay? So find all m by 1 matrices B such that the system of equations AX equals B is consistent. For example, let us consider here the linear system here. What conditions must be B1, B2, and B3 satisfy in order this system here to be consistent? For this, look at this. We have 3 equations and then 3 unknowns, x1, x2, and x3. So you have here a square matrix of coefficients. So you can check whether this matrix of coefficients is invertible or not. If it is invertible, okay, if it is invertible, then definitely this system is consistent. That's based on the equivalent theorem, the equivalent statements theorem that we have. If A is invertible, then a system will have the square. This is a square matrix. I mean, that's the matrix of coefficients. So if the matrix of coefficients is invertible, then the system will be consistent. However, if this matrix of coefficients is not invertible, then there's a possibility that the system has no solution. The right-hand side here, these are some numbers. So we will try to find conditions on this right-hand side so that we will have a solution for this system. To do that, we'll just do our Gauss-Jordan method. The augmented matrix will be 1, -2, -1, B1, -4, 5, 2, B2, -4, 7, 4, B3. So this is the augmented matrix for the system. So of course, we just need first to find the reduced row echelon form of this. Okay? And maybe we don't actually need the reduced form. We just need, at the very least, a row echelon form. So let us look at that. So this is 1 here. We can take row 1 as our top row in the process. That's your step 1. It's already a leading one, so we can skip step 2 and step 3. Okay? And then in here, this is 4, this is -4, this is -4, so we want to make these two guys here 0. And to do that, we just need to do row 4 plus 4 row 1. Sorry, row 2 plus 4 row 1. And row 3 plus 4 row 1. So if we do that, of course, row 1 will be fixed. 1, 2, or 1, -2, -1, B1. Row 2 plus 4 row 1, that's -4 plus 4 times 1, this will be 0. 5 plus 4 times -2, so that's 5 minus 8. 5 minus 8, that's -3. 2 plus 4 times -1, so 2 minus 4, that's -2. And then you have here B2 plus 4B1. So B2 plus 4B1. For the third row, -4 plus 4 times 1, that's 0. 8 plus 4 times -2, so you have 8 minus 7, sorry, 7 plus 4 times -2, so you have 7 minus 8, that's -1. In here you have 4 plus 4 times -1, that becomes what? 4 minus 4, that's 0. Okay? And then, what else? We have here B3 plus 4B1. Okay? And then, since this is already 0, we can just interchange the two guys here. So, in here, okay, we just interchange row 2 and row 3. So, we will have 1, -2, -1, B1. And then we will have here 0, -1, -2, and then, sorry, 0, -1, 0. And then B3 plus 4b1. And then we will have here 0, -3, -2, b2 plus 4b1. Then we can multiply this by -1. We'll end up with, so negative r2. So this is still 1, -2, -1, b1, 0, 1, 0, minus b3 minus 4b1. Then we just copy this. We'll end up with 0, -3, -2, b2 plus 4, b1. And then in here, we can just now add r3 plus 3r2. Okay? So r3 plus 3r2. Let me just reduce the size in here. Okay? But you will see that in here, okay, we will actually get an invertible matrix in here. In fact, if we just computed for the determinants of this, well, at this moment, we don't know how to compute for the determinant of a 3 by 3 matrix. That's why we are still doing this. But had we known, okay, how to compute the determinant, we can just calculate for the determinant of this matrix. But at this point of our course, we don't know that yet. That's why we are doing this. Okay? So, we do this R3 plus 3, R3 plus 3 R2. We will have, so we just copy 1, -2, -1, and then we have here B1. We also copy this 0, 1, 0, minus B3 minus 4B1. And then here, this becomes 0. And then minus 3 plus 3 times 1, that's 0. Here, you'll just have minus 2. Okay? And then for this part, you will have B2 plus 4B1 plus 3 times negative B3 minus 4B1. Okay? And then, if we continued with the RREF in here, okay, we will see that this guy here will just be the identity matrix. Okay, we will see that this is just the identity matrix. So I will continue with that guy. So anyway, we will have we can do this. We divide by -2. So 1/2. Okay, so -1/2 R3. We will have here still 1, -2, -1. And then B1. R2 will still be 0, 1, 0. And then minus B3 minus 4B1. Okay. And then here, this will be 0, 0, -2. Okay. Sorry, divided by 2 or divided by -2. This is 1. This guy here, you just divide it by 2. Okay. You can simplify this. in a sense that you have 4b1 here, and then here you have 3 times negative 4b1. Okay? So just try to simplify that. But what we will have is the following. So b2 minus 8b1 minus 3b3. And then you divide this by 2. Okay? And then from here, you can give this 0, and then you can give this 0. But from here, um, it will imply that, so from here, it will imply that the matrix of coefficients, so the matrix of coefficients is invertible. Okay? And this means that whatever B1, B2, and B3 are, this is always consistent. So the system is always consistent. Always consistent, whatever B1, B2, and B3 are. So for any B1, B2, and B3. B1, B2, and B3. Okay? The reason why we can conclude that this is already this is invertible, meaning this guy here from this point, the diagonal entries in here, the main diagonal entries, they are all 1, while these are already 0. In fact, 2 steps left. You just need to make this 0, and then this guy here to make 0. So you have the identity matrix for this side after doing those 2 steps. Okay? So that's this guy here. So whatever your B1, B2, and B3 are, this will always be consistent. Question? Now, what if we have this? X plus y plus 2z equals b1, x plus z equals b2, 2x plus y plus 3z equals b3. What are the conditions for b1, b2, and b3 so that this system is consistent? Same method. We write the augmented matrix 1, 1, 2, b1, 1, 0, 1, b2, 2, 1, 3, b3. Okay? And then we get the RREF. So instead of interchanging these, let's just make this 0 here and this 0 here because this is already a leading one. So for this, we can have R2 minus R1. And in here, you have R3 minus 2 R1. So we just copy first row, 1, 1, 2, B1. And then in here, we will have what? 1 minus 1, that's 0. 0 minus 1, that's negative 1. 1 minus 2, that's negative 1. And then we have B2 minus B1. Then for this, we have 2 minus 2 times 1, that's 0. 2 minus 2 times 1 here, 1 minus 2 times 1, that's negative 1. 3 minus 2 times 2, that's still negative 1. And then we have here B3 minus, so B3 minus 2B1. Now, looking at this, okay, 0, negative 1, negative 1. The third row is also 0, negative 1, negative 1. And then we have this. So what we can do is to do R3 minus R2. So we are now replacing R3 again with this. So we are just copying R1, 1, 1, 2, and then B1. And then R2, we'll just copy that. 0, negative 1, negative 1. B2 minus B1. For R3, we do R3 minus R2. So 0 minus 0, this is 0. Negative 1 minus negative 1, again 0, and again 0 here. And then in here, you will have B2, or B3, sorry, B3 minus 2B1 minus quantity B2 minus B1. Now, looking at this, remember that this is the column for X, this is the column for Y, this is the column for Z. And if you look at the third row, you just have 0x plus 0y plus 0z. Left-hand side is 0. Okay? If the right-hand side is not equal to 0, then you will have something like 0 not 0 equals not 0. So that cannot happen. Because if that happens, we won't have a solution for this. So, therefore, this system here, the system will have a solution, if this guy here, is also equal to 0. If B3 minus 2B1 minus B2 plus B1 equals 0. Correct? Because if that was equal to 0, you'll just have 0 equals 0, and there's no contradiction. But if this guy here is not equal to 0, you will have something 0 equals not equal to 0. And that's a contradiction. Understand? So these must be the conditions that we need. Okay? These must be the conditions that we need. So if we simplify this, we will have, or we have here B3 minus B2 minus B1 equals 0. Okay? So the conditions must be, so the conditions must be, you can choose any B1 and B2, but your B3 must satisfy this. So must be B1, B2, any real number, and your B3, this must be equal to B1 plus B2. This is the conditions that we need. Okay? So, the remaining slides here, these are all exercises. You will solve the system by inverting the coefficient matrix. We have it here, the same problem, but this time you have a 4 by 4 matrix of coefficients. And look at this. You have to consider this matrix A, and then of course the variable vector. You just need to solve for ax equals x or for ax equals 4x. So what would your solutions be? Okay? What should be those x? So that ax equals x, and then the other is ax equals 4x. And then one more set of exercises here. These are all proving parts. So I think you have all the techniques now so that you can prove this. Okay. And then, of course, you can do some more of the exercises from our reference book if you have a copy, or the file that I have uploaded, the SAGEP linear algebra problems. So you can also work on the problems there. Okay.